Hey, welcome to the next part of Chapter 9, which is calculating the moment of inertia. So when we calculate the moment of inertia, we are really looking at how the cross-sectional area of our figure or our object is grouped about some axis. All right, so the moment of inertia is very much about how area is distributed about a specific axis. So let me write that. So moment of inertia is how area is distributed about a specified axis. Okay. So this axis, the specified axis right here, could be a couple things, right? So it could be talking about how is the area of the cross-sectional area of the shape distributed about the x-axis or the y-axis. Or it could be talking about how is it being distributed about the centroidal axis. Okay. So it's a calculation that just kind of describes how area is distributed about a specified axis. Now, let me get out of brown back into, hopefully this is the right color, blue. The symbol for the moment inertia is I. You might see moment of inertia abbreviated as MOI, but when we're looking at the formula, it's an I. So I is the symbol of the moment of inertia. And I'm thinking really about a formula. Okay. A couple facts that I know about moment inertial or moment of inertia. A low value of I means that the cross-sectional area is grouped closely. So it is closely grouped. Oh, that's horrible. Is closely grouped about whatever our designated axis is. Right, so closely grouped about the x-axis or the y-axis or the centroidal axis. Conversely, if the value of I is high, so you have a high value of I, the area is located some distance. Well, I completely forgot that. Area is located some distance from the designated axis. Again, whether that's the x-axis, the y-axis, the centroidal axis. Okay. I have also heard the moment of inertia described as how likely it is for something to bend. Right. So we'll kind of keep that in mind as well. We're going to be looking at a table in the back of the book is where our formulas come from. It's table A2. Let me write that up here. We will be using table A2, which is on page 455, textbook page 455. And you're going to see two columns there. Two columns. And you say, well, that's weird, Rick, because you just talked about how area is distributed about a specified axis. It could be the x-axis, could be the y-axis, could be the centroidal axis. No, and I didn't lie to you. I mean, those things are true. The two columns that we see in our book are IX. So this is about the x-axis. So if we're asked to find the moment of inertia about the x-axis, man, we're using the IX column. There's another column there, IXC. And this is about the x-axis. Well, let's change that. Let's change it to the centroidal x-axis. Centroidal x-axis. Okay. So there's only two columns. There's an x-axis. Hey, if I'm looking for the moment of inertia about the x-axis, bam. If I'm looking for the moment of inertia about the y-axis, or I'm sorry, about the centroidal x-axis, bam, those are the two columns, okay? Now, what about if you're being asked to find IY? What if we're being asked to find the moment of inertia about the centroidal y-axis? What do we do then? What do we do then? So, yeah, so we will talk about that as we work our very first problem. I'm gonna pause so I can erase the board. When we come back, we'll do our first problem. Be right back. I didn't mean that. All right, thanks for your patience. I've got our first problem written up there. The problem statement for this is going to be calculate four things. Okay, so we're going to calculate the moment of inertia about the x-axis. We're going to calculate the moment of inertia about the y-axis. The moment of inertia about the centroidal x-axis, and the moment of inertia about the centroidal y-axis. Right, so that's our problem statement. So we've got to figure out the centroidal axis to do this. Now this is a symmetrical shape, so by inspection, I'll write that over here. By inspection, the centroid is located at 1.5 feet, 4 feet. So perfect symmetry. So I can just take the middle, 1.5 and 4 feet. Happens to be exactly right here. Okay. This is 4 feet, and this is 1.5 feet. Okay. We could go through the whole calculation, take the area, follow the rules from the table, take the summation area, take the summation of the x bars or the a x bars, the summation of the a y bars, all those things, but we're going to get 1.5 feet and 4 feet. Okay. All right. So step number one. So our first step is to calculate. Well, what are we asked to do? We're asked to find moment of inertia about the x-axis. So we'll just kind of go through this. There's four things we're asked for, so we'll just go through all four. Moment of inertia about the x-axis. So looking at table A2 on page 455, this is a rectangular shape. The moment of inertia about the x-axis is bh cubed divided by 3. The base times height cubed divided by 3. So the base is 3 feet. Height is 8 feet cubed divided by 3. Let's see. So the 3's would, well, I'm sorry, we're not going to do that. So 8 cubed. 8 cubed is 64 times 8. 64 times 8 is 320. Let's see. So it's 480 plus 32 is 512. 512 times 3 is 1536. So 1536 feet to the 4th divided by 3, which is equal to 512 feet to the 4th. It is a coincidence that the base and the denominator are the same. So if you're a pattern person, always looking for a pattern, it is a coincidence those two are the same. What is not going to be a coincidence is the units for inertia have an exponent of 4. Okay. All right. Now, this is not in the chart. It is in the book. Some folks find it difficult to find in the book. So listen and watch. To find the moment of inertia about the y-axis, all we do is shift where the exponent is in the formula. Same formula, it's still base times height over 3. We just shift where the exponent is. So notice that I'm going to calculate the moment of inertia about the y-axis. I've moved the exponent from height to base. Okay, so 3 feet cubed times 8 feet divided by 3. Well, 3 feet cubed is 27 cubic feet. 27 times 8 is 160 times 56, which gives you 216. That's equal to 216 to the 4th. 216 feet to the 4th divided by 3. And I'm going to use the calculator for that one. That equals 72. Okay. So in the moment of inertia in the y direction is equal to 72 feet to the 4th power. Put a check mark because we got both of those. Bam and bam. Okay. So the next thing we're asked to do is find moment of inertia moment of inertia about the centroidal x-axis. Okay. Moment of inertia about the centroidal x-axis. And I'm looking at the table, and the formula gives us base times height raised to the 3rd divided by 12 this time. I'm not afraid to divide by 12. Base is still 3 feet. Height is still 8 feet. I'm going to erase that exponent and put it where it needs to be. Which of course is on the outside. Divided by 12. So 8 times 8 is 16. I'm going to just do the calculator. 8 raised to the 3rd is 512. 512 times 3, 1536. Which we knew, right, from above. 1536 feet to the 4th power divided by 12. Should be something like 128 is my guess. 128 feet to the 4th. Then notice how the number has gone down. Notice how the number has gone down. We said that the lower the moment of inertia was, the closer it was, the closer that the area is more closely grouped about the x or the axis. The area is more closely grouped about the centroidal axis than it is the x and the y axis. So of course we would expect that number to go down. Our last calculation is the moment of inertia about the centroidal y axis. So remember that we use the same formula, we just flop the exponent to the other dimension. The first time I saw that, it freaked me out a little bit, but then I was like, okay, it perfectly makes sense, because I mean, essentially, what if you turned the object 90 degrees? So in my head, it makes sense anyway. 8 squared, or 3 feet raised to the third power times 8 feet divided by 12. That's still going to be 216 feet to the fourth. This time divided by 12, though, which should give us something like 18 feet. Yep. 18 feet. It is a lower number than we got when we were looking at the y-axis, because the centroid axis, there's more area close to the centroid y-axis than there is to the y-axis. So that's kind of the deal there. All right, so I'm going to save this video, stop recording, erase, and get the board set up for the next thing. Be right back.